For our second review, problem number 1 is a great College Board question. In a huge surprise, they actually do something that's somewhat rare. They actually give you the Maclaurin series for e to the x. So they write e to the x equals 1 plus x squared over 2 factorial and so forth. And then they're giving you this other function that's going to be based like this, e to x minus 1 quantity squared minus 1 all over x minus 1 squared. They're saying x cannot equal 1, but when x does equal 1, it will be assigned a y value of 1. It's a piecewise function, in other words. The function f has derivatives of all orders. Look at part A. They're saying write the first 4 non-zero terms and the general term for e to the x minus 1 squared for x equals 1. Now, of course, we have this formula right here that, of course, we should have memorized. We're asked if we could, for part A, make a Taylor series about x equals 1. Definitely we can do that. For part A, what we're going to do is simply substitute in wherever we have an x, we're just going to replace it with x minus 1 quantity squared. So you can see it's like having little spaces here. We'll just put in x minus 1 quantity squared. Here's x minus 1 quantity squared, but the whole thing gets squared here. We'll have x minus 1 squared, but now we're raising that up to the third power. Dividing by 6, which is 3 factorial. We're even asked to go to our nth term, but we'll have x minus 1 squared. We're raising that up to the nth, dividing by n factorial. And we can definitely clean this up. Whenever we're squaring a square here, this would become x minus 1 to the 4th all over 2. This next term would become x minus 1 to the 6th all over 6. And what about our nth term? We'll have x minus 1 to the 2n all over n factorial. It's very important for us to confirm why we can do this. We're making a substitution, but in a super important point here, they're asking us to be around x equals 1. About x equals 1, that means we are centered around 1. So every expression with an x raised to a power, it must be x minus 1 raised to a power. And that's why we can just do a direct substitution here. So part A, they asked for us to get those first 4 terms and the nth term. We have that. And it is a Taylor series about x equals 1. For part B, this might seem to be the most strange part. Many kids in the past have said, didn't we just do this? Use the Taylor series to write the first 4 non-zero terms and the general terms for f about x equals 1. Well, please realize we haven't done that. F is actually a very different function. It's way more complicated. And, for f here, we're going to have to do some work. So I'm going to go down here, and here's for part B. F of x is really e to this x minus 1 squared minus 1 all over x minus 1 quantity squared. But I want to point out that the e to the x minus 1 quantity squared, that's what we just did. That's for part A. That's where we can say, you know what? I do have a Taylor series centered around x equals 1 for that. So what you do is you make that huge substitution. We're going to have an infinite series here. Infinite number of terms. I'm just going to write that down here. We've got our first 4 terms that we're writing out just this way. And then, of course, we're going to have our nth term just as well. We'll have this x minus 1 to the 2n all over n factorial. But that's e to the x minus 1. Then you got to say this is your minus 1. And then down below we'll have x minus 1 squared. So you can see what's happening here. We're actually dealing with this situation where of course we have to do more than just work with that e to the x minus 1. We're going to have to subtract the 1 and then divide by x minus 1 squared. And I guess what I want to point out to you very quickly is, they're asking for us to have 4 terms here. I do want to point out the next term that we would have had in part A would have been x minus 1 squared to the 4th divided by 4 factorial. And why do I bring that up? Well, that would be x minus 1 to the 8th all over 4 factorial. I'm bringing that up because if you're really on your toes, 4 factorial, by the way, is going to be 24. You're going to see what's happening here. You're going to notice that the 1 and this minus 1 cancel out. That's going to be completely gone. And then what? Well, what's left is this infinite expansion. It goes on forever and ever. But this is going to become like the ultimate I heart math canceling. Every one of these terms is going to get x minus 1 squared divided out. So what are we left with? Well, x minus 1 squared divided by x minus 1 squared is just a 1. This next term right here, I'm going to lose x minus 1 squared. I'll just have x minus 1 to the 2nd. I had 4 of those factors. I've just lost 2 of them. I have x minus 1 to the 6 over 6 right here. I'm dividing out x minus 1 squared. I'll have x minus 1 to the 4th divided by that 6. This is why I pulled out this extra term here, because they're asking for us to write the first 4 terms, first 4 non-zero terms. We had to go one step beyond. When I take x minus 1 to the 8th divided by x minus 1 squared, we'll have x minus 1 to the 6th. Then what? Well, as we keep going, we're going to notice that this nth term, what's going to happen is we'll have x minus 1 to the 2n minus 2 divided by n factorial. And of course, this would be for a sigma that would be starting at n equals 1. This is our answer for part B. We've got our first 4 terms. We've got a general term. Well, we could have changed our nth term too. And sometimes on a College Board rubric, they will write this in an altered way. I do want to say that, this series, maybe just making an extra comment here, to make this work, you'd have to be going from n equals 1 to infinity with this nth term. And that's fine. Can definitely have that. Do want to say that the College Board will sometimes, as you look at their grading rubric, actually bump up every power of n started at n equals 0. So an altered form that we could have had, just good review, would have been, bumping down your counter to 0. You're going to have to bump up n by 1 everywhere else. So, just talking about this, some good review. This is an even number. The next even number would be 2n. But that's just, some good review about different ways to represent this. You could have what I've just circled here as your nth term, in other words. Well, let's keep going. For part C, they want you to use the ratio test to determine the interval of convergence. And my word, as you're trying to work out this ratio test, let's go to the n plus 1 term. The n plus 1 term means go one step up. By the way, we kind of were talking about that just a moment ago. We'd bump this up to the next even number. We'd have x minus 1 now to the 2n. And down below we'd have n plus 1 factorial. This is working off of the nth term that we have right here. This would be your n plus 1 term. Then we're going to divide by the nth term. That would be this thing itself. So we'll have n factorial over x to the 2n minus 2. So we could have done this problem differently, working with this other nth term, and then we'd have to bump that up by 1. Just letting you know, there are a couple of different ways that can be worked out. But regardless, this would become n plus 1 times n factorial. These would cancel out. If you're really thinking about it, you're going to have, and I should have written x minus 1 over here. You can see that really we're going to have 2 more factors of x minus 1 up on top. So this would be x minus 1 squared. Now the cool thing is, when you're squaring something, you're going to notice that, in all honesty, you don't need the absolute value around it anymore. You could just lose the absolute value altogether. And you really are left just with this x minus 1 squared over n plus 1. But as n goes to infinity, this denominator grows to be very huge. X minus 1 is a real number. Divide by something huge, you get 0, which is less than 1. Your interval of convergence is all real numbers. So that's for part C. So we'll go from negative infinity to positive infinity. For part D, they're throwing in some general calculus review. And they're saying, use this Taylor series for f to determine whether the graph has any points of inflection. So what we're going to have here is, going back to B, you might know that when we're investigating points of inflection, we need to take a second derivative. So that means first we'll take the first derivative of 1, and I'm just working, of course, from this series up here. I'm going to take some derivatives. As I take my first derivative of 1 goes away, then I'll get 2x minus 1 all over 2. You can see those 2's are going to wipe out. Here we'll have 4x minus 1 to the 3rd all over 6. Here we'll have 6x minus 1 to the 5th all over 24. And then we'll have 2n, well, have some space in here for the nth term. 2n minus 2 times x minus 1 to the 2n minus 3. And this is going to keep going. Well, let's go ahead and take our second derivative. So we do that, second derivative, you can see that this is just going to be a 1 as I take the derivative of x minus 1. Here, I'm not even canceling. I'm just, making some observations. I'm bringing down the 3. We'll have x minus 1 squared. Here I'll have 6 times 5, which of course we know is 30. You're going to drop your power down. Coming over this way, you're going to have 2n minus 2, but now you're going to bring down 2n minus 3. And your new power, you're going to drop it down by 1 as well. Well, you're looking at this, and, hopefully what you can see is every power of this expansion is even. And we start off with a 1. What we can say is, since every term is non-negative, we can say with confidence that our second derivative must be greater than 0. Therefore, f is always concave up, and doesn't have any points of inflection. And that wraps up this very important first problem.